Right, great. So I'm so happy to have Jan Camenisch with us as part of our World Leaders in Cryptography series. Hi, Jan.
Hi, Bill. Happy to be here.
Yeah, and it's great to have you. I think on my website, I probably have more of your papers implemented than of any other cryptographer, maybe apart from obviously Ravesh Shamir and Edelman. So Jan is a CTO and cryptographer at Dfinity, and since 1998, he's consistently produced research outputs of rigor, novelty, and sheer brilliance. He was recently awarded, along with a co-researcher, the Levchin Prize at the Real World Cryptography Conference 2024. Jan's research core happened when he was hosted in the IBM Zurich research labs and has since moved to Dfinity. But he has still continued to produce research outputs that are some of the best in the world in the whole series of computer science research. Overall, Jan has published over 140 widely cited papers and has been granted around 140 patents. He was also received the ACM SIGSA Outstanding Innovation Award and an IEEE Computer Society Technical Achievement Award. One of his key research outputs related to the CL signature, which we'll discuss later, and which allows for a privacy-aware digital signature, along with many other contributions, such as range proofs, oblivious transfer, and privacy-aware identity mapping between domains. So, Jan, what's your current role, and what does a typical day involve for you?
Yeah, thanks, Bill. Yes, as you said, right now I'm CTO at Dfinity, so I'm responsible for like all the technical aspects, getting the implementation, designing the internet computer protocols, contributing. So it involves like a wide range of activities. But I guess in some sense, my typical day, like on one hand, looks very boring. Like I drive to the office, maybe get to do some sports in the morning, like work like crazy, drive home, spend a little time with my family, and do some more work, and then drop that. But like I said, on the other hand, like every day looks pretty much different if you look under the hood, like what's going on. I mean, it's like very startup-y in the sense that, of course, like as a CTO, you do some like management chores, right? You need to tend to your teams and all of that, but then it's also like a lot of this really going on. Think about like what we should build. In some sense, like as a startup, you have to reinvent yourself almost every day. And I mean, of course, it's like it's a ton of fun, but it's also not easy because being like at a startup is like it's non-trivial. A lot of them fail, and so if you don't want to fail, you have to really reinvent like every day.
That's good. And where in the world do you live?
Well, I live just outside of Zurich, and our offices are like in Zurich, like at the city. And so it's like also that is nice, like working in the city. It has well pros and cons, but just go out and like out of your office, you feel the life around there.
That's fantastic. I know it's a very beautiful city. I live and work in Edinburgh, and that's also a beautiful city. But I think Zurich is one of the best places in the world to live. Great. So, what were your school days like? Were you a great pupil, or did you not like your studies?
No, I did because well, maybe we go and speak about Divinity a little bit more later because like I also realized like when I talked about like my typical day, maybe most people really don't know what I'm doing right now, right? And, so maybe let me go a bit there first before
That would be great. Yeah,
answering
yeah.
question, if you don't mind. Um, so because Divinity is a foundation, like, which is very typical for like the blockchain space, and it's a foundation that created the Internet Computer Protocol. It's like a blockchain, And like our vision here is to run all the world software on blockchain. It's like a paradigm shift how you can build a secure computer system, really. You know, like traditional computers were like this, whatever, maybe started with pocket calculator, this kind of thing, and then there's like more powerful pocket calculators. Well, either when became a mainframe, which were also standalone, but at some points they got connected and so on. It's really computers that we all use today, but none of that was built with security in mind. And I think like the blockchain space is really taking this radically different approach, where you say like, how can we build a computer from a protocol, right? I mean, and like Bitcoin sort of proved that, and I mean, of course, all of the more maybe sciencey, computer science, but system people work like know that like distributing a system is a way to make it more secure, more reliant. But I think that the world only realized that like when Bitcoin came along and really proved that point, right? Like Bitcoin is a protocol that can be run like it's very, very different places, and it gets security from that because it is a protocol. You know, you cannot not hack into it because like there's like other people out there who run the same protocol, and so that's what makes it secure. And I guess as we all know, Bitcoin is not very efficient, right? It's like it eats energy like nuts, like whole countries. But the principle stands, right? And so like I think now so at Dfinity we have set out to you know like build like a whole computer, full powerful computer, and like the system is up and running since 3 years, and but we'll be busy extending that for the next 20 years at least, right? I think my whole the rest of my whole professional life plus some more of that. Again, I could speak forever here, but maybe let's go
Yeah,
back.
yeah, we'll come back to that. And
Right.
I really understand the whole focus and how poor our computing systems are based on this von Neumann architecture, and everything is untrustworthy. But we'll come back onto that. So what were your school days like?
Yeah, sure. I guess you know, like I prefer speaking about my work rather than my life. But anyways,
Mhm.
I'll give you some insight here. So I grew up in a very small village up in the Swiss mountains somewhere. We like I mean, like we lived like outside, even like 2 kilometers like away from the school. So like the next neighbor was like a few hundred meters away. And so what I remember from my school days was that like on the one hand, like you know, like you go back and forth to school, like for like the morning lunch break and so on, was like and one way was like more than 2 kilometers, like even in winter with tons of snow, that those times still happen. Sometimes you had like 1 meter, 2 meters of snow, like almost overnight, sometimes really literally overnight. So I remember a lot of that, right? And then school was like this small village school where we have like a ton of classes together, right? I mean every class had the like the different grades. And I think I remember, I guess on one hand it was nice because you got to hear also what the three grades like above you would can learn. So you guess in some sense you have like ample input to learn and to yeah to enjoy learning.
That's good. And what sparked your interest in maths and cryptography?
It's really hard to say. Like when I try to remember, I couldn't point like at a particular time. Like like if I remember, I mean, I've always been like an engineer. I like to build stuff. And so I grew up on a farm, right? On a farm, you do always do practical work. Of course, like in summer, there was a lot of like farming work that you got to do. But it also gives you like a playground as well, right? There were always tools. There were always like wooden boards, like stuff you could use to build stuff. Yeah, I think that sort of formed me probably, like use your hands to build something, and math sort of, in some sense, also it's a tool. You can build something, but like I don't know, in your head. And the cryptography is sort of the nice thing where you can use like cool mathematics to do cool stuff. You can really, get something. You build something that's actually useful. That can be used like an encryption scheme kind of thing, or like a lot of like the work I did around privacy. It's like, you can build stuff that sort of seems unachievable, seems mind-boggling. And of course, the greater is the satisfaction if you manage to build something that seems mind-boggling, right? So you can sort of solve problems and get great satisfaction out of that.
Okay, and you ended up in IBM Zurich. What was your path that took you to that from school into that research environment?
I guess school you refer to university.
University, yeah, your
It's primary
undergraduates and
school. It's a
PhD.
very long-winded road.
Yeah.
Um, well, I guess like I studied actually electrical engineering, and then sort of realized that I really want to do like I did summer jobs at like some different electrical engineering companies, actually built modems at some point, like from like assembly languages, soldering circuits together, and all of that, which was really like enjoyable on the one hand, but on the other hand also seemed like a little bit too straightforward, and so like I wanted to do more. I wanted to do research, and so that's how I ended up and still enjoying mathematics. So I thought, okay, I want to do like research. I want to do a PhD kind of thing because that gets you to do research, do new stuff that people haven't done before. Yeah, I guess I was fascinated by coding theory because that's what you get taught or at the time did get taught at engineering schools. But then there are I guess it was Jim Massey, which is like a famous coding theorist. But he was about to retire, so wouldn't take any students. But then somebody pointed me out to like one of Jim Massey's students, which is Uli Maurer, and told me, this guy just started over in computer science, and he might take some students. Well, it's cryptography, but it's quite close to coding theory. You might enjoy it as well. And so I went there, visited him, and yeah, I guess then ended up doing cryptography and really liked that. I think eventually that's also like I think why I ended up at IBM Research, because I wanted to continue doing research. I guess spent a year in Aarhus University, but then somehow like my wife at the time wanted to go back to Switzerland, and IBM had an open position, so I applied and spent like 19 years there.
And the good thing is that coding is now coming back with post-quantum cryptography, but we'll come back onto that a little bit later. And so IBM are and were a world leader. I think they hosted Horst Feistel with the who created the DES cipher in the US. So the Zurich labs again produced some amazing work. What was your memories of working in the team there?
I have very fond memories. Like, I mean, otherwise I would not have, not have stayed 19 years, I guess. But I mean, like we had a great team. Of course, the team changed also over the years. But like, it was always a great team, a ton of like fun people to work with, and it was like, I mean, I guess IBM Research is almost like a university in terms of, so for people who don't sort of can picture this, but it's like maybe you do like the research you like to do minus the teaching you have to do at the university. So that's about like how IBM Research was, or I guess still is. It's like this campus outside of Zurich in like green area, right? You can like if you want to do a jog over lunch, that's perfectly possible. Just get out of the door, do some jogging. It's like very quiet, but like also like like quiet place to for people to work together, get inspired, and have a great time.
That's great, yeah. And you could have stayed in academia and obviously became a professor, but you moved into industry. What was your motivation of moving, taking that direction for your career?
Well, I don't think I thought a lot about it. I guess we just want to go back to Switzerland at the time, and actually, I also like applied at the APF Lausanne, and I guess after I got the job offer from IBM, I also heard actually Lausanne would also have given me an offer, but then I already took IBM, so there I was. So I don't think it was a conscious decision. Um, but having said so, I think there's like I said, it varies, but I think industry has a bit of a, or at least IBM research. I would generalize to industry in general. I think it really depends which research lab you're doing. I had this thing like I think many like university have like tenure, and so you work very hard. Most people burn out during those first 6 years, and then hardly do anything thereafter. Whereas IBM, it was sort of like more like a constant pressure to do stuff. So it was not like just fail quickly and burn out kind of thing. Um, but again, I think I enjoyed it. It was just, I mean, sometimes it just happened, and it was like perfectly fine for me.
Yeah. And obviously, at Definity, you said that you're working on this internet computer. So this is a way that we can actually start to trust all our transactions. So everything that happens in the computer is auditable and can be trusted. So how do you think we'll migrate from our existing untrusted world where we have these naive protocols that were designed for the internet that were really just host to host communication protocols. How are we going to migrate from that completely untrustworthy world towards something that would be as you define the internet computer?
Well, I guess it will be step by step, right? I mean, we have like large software systems running, right? And many of them still run on Cobalt and whatever these programming languages are called, Cobalt, I guess. And so it will be step by step, right? And it's like what we've seen right now, like the digital assets, maybe some financial transactions, like something where you want to have like high security, high assurance. I think that these will be the first applications. But I think on the other hand, like there's teams who have built like complete like chat application, essentially like a clone of WhatsApp on the on the internet computer blockchains as well. So that's totally possible already today. So a user can just fire up a browser and it will be talking to a smart contract. So it's like the highest levels of security, and be able to chat with people in real time. So it's I think the capabilities are there. It's more like, of course, if you have a running system, like migrating to a different platform is like a huge step. So it will take a long, long time. It's like, like now you have fast cars, but people are used to horse carts, right? I mean, how do you migrate from that? So it's a step by step. Like some people then use the new things, and it will take time. But it's going to be exciting times. I'm really sure about that.
Yeah. So we have Ethereum, and obviously that provides you with a layer one, layer two type blockchain. Do you then build the whole computing infrastructure on top of your own blockchain? How does it actually operate? How do programs run? How would users submit their tasks for the internet computer to perform?
Yeah, so I mean, I guess the our vision is in some sense, I mean, very clearly like to like not have like Ethereum or Bitcoin in the picture really. So like the goal should be or is that like all the world software really runs, or like almost all the world software really runs on the internet computer. because you can't really run stuff on Ethereum, you can't really run stuff on Bitcoin. Now, having said so, right, I mean, I think Bitcoin has like a few advantages, like being proof of work that might be useful. Same for Ethereum as a large ecosystem. And so as we talk about migrating, I think we will see like a lot of things working in parallel, right? And I guess that's also what we're working on at Dfinity to make sure you can have the best of both worlds, right? So that you can have some things on Bitcoin, you can transact Bitcoin on the internet computer, you can tap into that proof of work security as well if you desire to do so. I think at the end of the day, like the world needs to be interoperable. Like if you have like a walled garden somewhere, like that's not a lot of fun. So you need to have operability with legacy system, new system, Ethereum, Bitcoin, like anything of that, and that's like very much design criteria of what we try to build. That this is actually possible. You can just like like have a smart contract that talks to other smart contracts, another chain that talks to legacy database. So like all the smart contracts on the internet computer can actually talk HTTP in and out. They can sign cryptographic transactions and stuff like that. So I mean, in many ways, that they're like really more powerful even than traditional software. They have like the same power, but then they're just based on like run on a more secure platform. They're like an extension of the protocol. And also that makes implementations like in some sense easier because you don't have to worry with like all these like firewall security kind of things that you have to worry about like, with traditional systems.
Okay. And what was your favorite research paper that you published and why?
Yeah, blast from the past, I guess.
Mhm.
Different from like I think at Dfinity we don't well we actually do publish things, but it's mostly about you invent cool new stuff, you do cutting edge research and get it out into a product like 6 months, a year later. But I mean I do appreciate all the papers. I guess they it's really hard to say which one is my favorite ones in some sense. Like they're like kids, right? I mean it's like they're all my kids. I love them all. They're all great. Normally, I guess it's just the latest one you're still working on because that's the one where your whole heart goes into. But now, like I haven't been working on papers, writing papers too much lately. So maybe there's a bit of like distance to some of those papers. Maybe it's like a signature scheme with sufficient protocols that I wrote with Anna Lisianskaya. And the reason probably is like, I mean, I did not get published like at the top-notch cryptography conference. It got published at this smaller conference in Amalfi, which is like a lovely place to have a conference. But the reason I like it because it sort of, like a lot of my research agenda was towards like building cryptographic protocols, building systems, like what I'm doing now at Dfinity, right? Like building something that you know it's secure, that's mind-boggling, and very often you have building blocks for that, right? Because like well, the smallest building was probably your like cryptographic assumption, like your discrete log problem or your whatever learning with error problem. And then you build stuff from that, right? And then you come up with signature schemes, right? And encryption schemes. But they by themselves are, well, you can use them as such, but when you want to construct like a larger protocol, then you need to base on that, right? And so there's like two versions to do that. Either you could go into full-blown multi-party computation, which sort of can solve any problem, but then that typically is not efficient. And so when you want to have like efficient systems that you can actually use in practice, you need to have like building blocks that you can combine more effectively. And so that's why I guess this signature scheme with efficient protocols really that. How can I sign something, but then use that signature like in other contexts? How can I prove stuff about it? How can I like, and of course it goes to this like anonymous credential systems, right? But like that's one way to do it. If I have a signature on some attributes, like a credential, and then later on I prove that I am over 18. And then so that's exactly what the underlying thing here is. Like you need a signature scheme with some protocols around it that allows you to efficiently prove that you're over 18. Of course, that is a generic statement, which again you can prove generically. But if you want to prove that efficiently, then you need to have like more specific protocols just tailored to that task. And it sort of turns out like you can have like a kind of building block kind signature schemes, so special zero knowledge proofs that really come together nicely that allow you to build systems such like credential systems. And so that's why I like this paper, but was sort of, I guess, never really. So it was not accepted at these bigger conferences because they were somehow the community didn't really like to accept these building blocks because I don't know, they didn't see the value. Whereas for me, unless you know, like this, it is these building blocks that actually enable it, and so that's why maybe that's the paper I like the best.
Yeah, I love that paper too. And really it's probably, as you say, you're taking something that was designed to be centralized and now you're breaking it up into little parts and no one can see how the parts all work together. So we'll come back onto that. So I think in 2003 you worked with Victor Schupp on verifiable encryption, and it's a technique that's now coming to the surface again. Can you just outline, if you can remember, how your method worked?
Yeah, totally. So, I mean, that paper also is like another puzzle in that toolbox, right? Before we talked about the signature scheme and how can I do stuff with the signature scheme, how I can prove something, right? But now the problem is, okay, so now I've signed something, or I have something and I want to encrypt it and then prove to you that I encrypted the right stuff, right? I mean, and what encrypted, I mean, it could be like somebody signed it for me. So, like let's say we have this, a proof that I'm old enough, right? So I have a signature on my birth date, right? And then I do like a zero knowledge proof that I'm over 18 or something. But then maybe there's like the circumstance where somebody says, well, actually, but if something goes wrong here, right? Whatever. Let's say I'm entering a club, totally contrived example here. I'm entering this club. I prove that I'm over 18, and then everybody had a good night and goes back home. But then like that then somebody finds like this dead body somewhere in that club. Now suddenly you need to investigate, okay, what happened, right? And now you need to have more information about all the people in the club. And so maybe the protocol should be, well, okay, you can enter here anonymously, you're over 18, all is good. But in the case that something bad happens, maybe the police should be able to like still find out what your name is, right? And so that's why you say about like here is like an encryption of my name that also was contained in this like certificate in this like signed. And so now I need to prove you that okay, here like this encryption contains my name that was also signed by the issuing authority. So that was the motivation about that paper, right? And then I guess like Victor and I again, we met at IBM and worked together like for many years at IBM. And of course, then like you start discussing these problems, right? And the sort of okay, how can we do that? And I mean, Victor is, I guess he is known for many things. There's probably like if you mention that like a cryptographic topic to Victor is probably the one who's written a paper on it or can easily write one on it. He might not have written all of them, but he totally could. And so we discussed that, and I guess Victor did like the Kramer-Schrupp encryption scheme and so on. So we kept discussing, and of course there we go. There was we came up with a solution to a encryption scheme where you can easily also prove that you encrypted something that you care about, like your name or something like that.
I think that was an excellent explanation of verifiable encryption. So you're one of the inventors of identity mixers. Could you just outline how they work?
Yeah, I guess identity mixer sort of, I guess also like a name for like I guess others will call it like a pseudonym system, a credential system, and I guess we called it like identity mixer to give it a bit of like a brand name. Like say, okay, here you have different identities all over the place and so on and so forth. And well, I guess in some sense, I mean, the inventor of anything privacy related in crypto is really David Chaum. Like is going back to his paper on traceable electronic mail, return addresses, and digital pseudonyms. And like I guess identity mix is really like a an implementation of that with like all possible bells and whistles. So it uses like verifiable encryption if you want to like address the scenario I was talking about before, but it was really like an identity management system where you can have different pseudonyms with different parties and then like get credentials issued on one pseudonym that you can then prove ownership on the other pseudonym. So that's why it's called the identity mixer, right? Like you sort of have like, I mean, I guess we all have not one single identity. We have like different identities. We know people with different names, like different attributes. And people maybe issue these attributes to you. And so the question is now, how can you transport that in an online world in a verifiable way? And so identity mix is really like a cryptographic system that caters for that. Because people would call it like whatever privacy preserving identity management system, something like that.
Yeah. And obviously, when you were at IBM, you worked with Anna and you created a range of CL signatures that were anonymity enhanced. And I think one was CL15, as I remember, which focused on an unlinkable signature. Can you remember what the problem was that you were working on for that signature?
Um, Tough question. I guess don't quite remember which one CL is because there were like CL like many.
17 and 15. I think the CL one was allowing you, if you're in one domain, such as in government, and then another domain, such as health, then I think it anonymized the identifier so that you didn't merge the identities together like they would normally do with governments, like
Yeah.
a tax and insurance number. I think that allowed you to keep the identities, and then you had this audit trail, a log that allowed the citizen to see who had been accessing your identity. It's similar to what they do in Estonia. In Estonia, they have an audit system that allows the citizen to see who's been looking at the record. So I think
Okay. You remember much
15,
better than I do.
yeah, I implemented it probably
Right.
sooner
Okay. Cool.
than you. Is that right? Was that paper?
That's probably quite correct, right? I think like I mean, as we discussed, it's like identity management system is price, right? I think we were working on a lot of those aspects. I mean, if you have like credentials, you need to revoke them. How can we do that? Then maybe you want to have like
Yeah.
signature scheme that
I,
is like more efficient. Then you want to have like, as I say, so some traces that people can investigate. You
yeah.
might, I guess we had this. I remember like another like the Clone Wars paper where it's about how
Oh
can you
yeah.
prevent people like sort of sharing their credentials and using them too many times. Because obviously, if you and I share a credential, then we both can use it. And since it's anonymous, it's really hard to like detect misuse. Whereas if I shared and I guess that's Netflix does that very much now. If people share the same Netflix account, they like, at some point they didn't care, but now they're sort of detecting that. Of course, it's easy to detect because it's both the same email address and the same password. But if you have like anonymous credentials, that would give you the right to watch Netflix. They couldn't do that, right? And so the question is, how do you control that? So there's like stuff like that. I mean, we were like, like talking about all these use cases and then having fun addressing them and giving them these papers like nice names. I remember like I think it didn't make it in the final version, but like I remember on, and I had like one paper where Alice and Bob communicating. Like one of the protocol steps was like they would go and have coffee. So I think you always like I think if research is not fun, if you're not having fun doing your work, you're doing something wrong.
Yeah, I agree. I think the paper itself used homomorphic encryption, but it was partial homomorphic encryption before we developed full homomorphic encryption. I think that's the way that you translated
Probably,
the
yeah.
identities.
Okay, cool.
So, so I think in 2007 you worked with Gregory Nevin on oblivious adaptive oblivious transfer. Oblivious transfer hasn't quite been adopted as we would have hoped at one time. But can you tell us how oblivious transfer works and what do you think the applications might be?
Sure, I can try. I mean, I guess Gregory Nevin and I guess he's the one I've written most papers
Mm.
with. We have really like a long, like I guess almost all my time at IBM, Greg was there as well, and so we did a lot of fun stuff together. And I guess oblivious transfer was also, yeah, you're right. It's like one of those primitives because you can even prove that from oblivious transfer you can like build like all the other cryptographic primitives. It's a very powerful primitive, but some of things are a bit theoretic, I guess. So I mean, like going back to like, do you solve a problem with multi-party computation, or actually do you solve a problem with like that actually has like gives you a efficient solution that you could actually implement and use in practice? And so actually for oblivious transfer, I mean, there is some use cases really here that would be sometimes interested in practice, like a query to a database, right? I mean, I want to query a database without you learning what I'm interested in. So for instance, think about a patent database, right? I mean, like so these patent databases, and I mean, these databases exist, right? And people sell you access to them. Extra services, but then just the fact that if you're interested in some particular pattern might give away something. Okay, this is now a hot topic, right? So you leak information. Here, like oblivious transfer, of course, is like has a practical advantage because now here's a parent database. I want to query some pattern. I pay for each query, but I don't want you to learn that. And I think the solution that Greg and I came up with in that paper was, so what if just like we like encrypted all those records independently and then sort of handed out the decryption key. And now the problem becomes, okay, so how do I get like an encryption key for a particular index if I know what index to look at? And so now it becomes like a problem of sort of evaluating sort of like some kind of function based on that index without like you and I, without you learning which index I'm using. And I just only learning like the evaluation of that index. And what we did in that paper was like we used like a blind signature scheme. So like and of course like here the signature has to be deterministic. If you sign a message, then you will always get the same signature, and then you can use that signature as a key. So the idea here was that you would like encrypt every record with like a signature on its index. Of course, you have to throw some random oracles on top of that to make sure that you get good entropy for that signature. But I think that's essentially more or less how that scheme worked. Of course, now it becomes tricky. It could be adaptive and so on. So there's like a few things that you need to worry about if you want to prove security. And like as usual, like I guess actually modeling things correctly is far from trivial. Like encryption is a good example, right? I mean, like I think so. Maybe now finally we have like a definition for an encryption scheme that it should really satisfy. I'm not sure. I guess maybe even there are some things that are not satisfactory, and I guess we can also talk about that later. But like this, the first encryption scheme wouldn't be secure if you encrypt your own secret key under it. All these kind of use cases, and so also in this paper, I remember like trying to find the right definition of security was like far from trivial. So it's much harder than come up with the idea for the solution. It was really making sure that actually it is secure, that you can model it correctly, you can prove it correctly.
If I look back at many of your papers, there's a magic wand in there, and I think the magic wand could be pairing-based cryptography. And obviously, one of the problems with cryptography is it can be difficult for someone to come into it and learn some of these magic wands, Diffie-Hellman method, RSA, elliptic curve, and so on. And they're not that difficult when you get into them, but it's just that engagement. So I don't know if it's possible for you to explain the basics of pairing-based cryptography uh, to an audience that maybe haven't come across it before.
Yeah, I mean, I remember that there was I think it was like Matt Franklin visiting IBM, and he told me about this pairing-based stuff, and he hears pairings. I thought it was very useful, and he explained it to me, but I wasn't able to. I mean, I guess I got the idea, but then like how it is, right? Like your mind is really like busy with other things, and so you didn't really dive in to understand the potential. I think he must have done the same with Dan Bonnet, and I guess I think
Yeah,
that is one of those guys. He very quickly sees the application, and so I guess then when I saw what they had done with pairing-based crypto, I said, oh, okay, wow, that's how it works. And then I guess that sort of then also sparked me to like use pairing-based crypto as a tool for many things, signature schemes, verifiable encryption, like the whole shebang. I think once I think it's really like you need to sit down and find the time to like have the peace of mind to explore some of those mathematical primitives to see what you can do. And I think like for me it was like when I saw like that paper, said, okay, so that's how I should think about it. And like it sort of did solved or I guess did that step for me that I wasn't able to do when Matt explained that thing to me at IBM.
yeah, that's amazing. Just today I was looking at curve 25519, and it has a co-prime of 8, and they do lots of fixing of it when it comes to the key exchange, but they don't do it within the signature method. And it's only when you really dive into some of the basics of the maths, of the orders of the curves are not prime, which causes all these problems that need to be fixed. And you kind of worry that some people are using these methods and just using them and not knowing some of the problems that lie underneath. So I don't know how we address this, but there's obviously a barrier between the research that's published in conferences and our education. Are we training software developers and engineers the basic mathematics and the techniques properly? Because they're really dealing with some serious methods.
No, I fully agree. I think like as a cryptographer, like we're all guilty to, abstract so many things away. I mean, it's even worse, I think, than what you're saying. Because on one hand, yeah, we like put all of those details under the carpet, but then also like when we do proofs, there's a lot of other things we put under the carpet, right? I think if you go to if you go to like, trained mathematicians, if they look at proofs that cryptographers do, I mean, they get shocked, right?
Yeah.
And it's just, I think it's also hard for like new people getting into cryptography. I mean, I guess the earlier on you got into it, then all the complexity theory, all those like 1 to the n kind of notation that sometimes people use, and you because no students wonder why are people writing 1 to the n. I mean, that's like really stupid, right? But I think it takes like unless you really understand it, unless you really have done these things, and in some sense, unless you really write down all those steps, you can never be sure. And because we just gloss very, very often just gloss over them, and the proofs are pushed to the appendices. People don't really care too much about those proofs. I think that there's I think there's like a few like wounds that should be tended to way better.
Yeah. Along with the CL signature schemes, I think your papers are typically referred to with the year. So CSS08 was published in 2008 by yourself. And I think in CSS08, you created a method where you can prove that you had a value within a series of values without giving that value away. And really, it was the start of zero knowledge proof. I think that the title was Efficient Protocols for Set Membership and Range Proofs, which is interesting. Can you remember the focus of the paper and how
Yeah,
that method's been used?
I think actually maybe the acronym might have been CCS because it's like Camenisch, Chabuni,
Oh,
Shil.
CCS. I'm so sorry. It's CCS, yeah.
Yeah, I think I mean this one also like was one of the papers for that toolbox, right? When you have like some signature, now you want to prove that you're like over 18 kind of thing, right? You want to show that whatever is contained your credentials in a certain range, and if you want to show it's over 18, I guess you want to show that your birth date lies further in the past than 18 years, right? So it's like this. We have like it's really like a SEP membership proof, and so I said that what was one of those papers where we had like new ways, like more efficient ways to do that. And right, so that's one of those like I guess many of my papers that like add to that toolbox, that improve on that toolbox, and so it's like it was like together with a student like Abi Shalad and the student and I did that, Rafik Shabuni, and because it was his master, I think master thesis, or because he started to do his PhD afterwards, so it was like a cool start from him, and then I guess like a cool paper. So it got accepted at Asia Crypt, something like that.
Yeah, it's true. I mean, I think you have created a toolkit. I think if you look in Hyperledger, you'll see that a lot of your methods are implemented in there. So you've worked with many great cryptographers. Who is the one that you learned most from?
Oh, that's a very difficult question, right? I guess I mean I really had the pleasure to work with many people, and it's really hard to say, right? I mean, at the end of the day, writing a paper, you're always like learning by doing, right? I think it's of course you're always profiting from each other. So like I guess I learn from them, they learn from me, do stuff together. And in some sense, I guess if I have to say with whom I learned the most, or from whom I learned the most, I mean, on one hand, like the answer has to be Gregory Nevin because I wrote the most paper with him. So in some sense, it's him. In other ways, maybe it's Victor Schub because like he is like some years older than me, so he was the more senior guy. So maybe I learned most from him. Or maybe it was like Anna Lisianskaya, who was like I had the pleasure to work like very early on in my career, and I guess she did her PhD at MIT, and so sort of like I guess I maybe came. I mean, I came from a different school like ETH in Zurich. And somehow I was also exposed. We heard some of the like the MIT thinking, whereas I guess the ETH thinking was a bit different. So I learned from her as well. I guess these maybe are the names that stand out, but like I think I had so many great other co-authors, and that I don't. I mean, it's too many to mention them all, but like I really enjoyed like them all really.
Yeah, and so well done for winning the award at Real World Crypto. I think Anna was the one who picked up the award. I think I saw a photograph of her picking it up.
I know I was there as well. I guess
Oh, you were there. Oh, that's
you
great.
know,
Yeah.
one of the I hadn't been at a cryptography conference because the last one before that was probably in 2018, so it was like a bit of like coming home, seeing a lot of like old friends, meeting some new friends even as well. So that was like, yeah, it was great. It was a surprise also. Like I did not expect it at all. It sort of came out of the blue, and the more fun it was to go there, and I guess the more humbled I am by receiving it.
Yeah. And it's good because your papers were quality, and you didn't necessarily focus on the ACMs or the IEEEs. You went and disseminated it at these conferences, and I think the Real World Crypto Award really highlighted the quality of the work overall. So, what does the next decade in cryptography look like? What are the key problems that we need to solve?
Yeah, let me get out my crystal ball. I guess well, maybe, but the key problems we need to solve that probably might not require a crystal ball. Um, yeah, so I mean, I think on one hand, it's really like quantum safe crypto. I mean, I'm a bit going back and forth with that because like a nice episode here is on my last day at Aarhus University, which was like I guess 99. I went to see the quantum computer there. I didn't want to leave
Wow.
the place without having seen the quantum computer, and they could store like 4 qubits for whatever. I forgot what fraction of a second, but that's what they could do. I think there were some entanglements as well. And like as you mentioned before, like IBM is also working on quantum computers and stuff. And same thing there. On my last day, I couldn't leave without having seen the quantum computer. And it's like 51 qubits. I guess these were like, if I remember well, logical qubits. It was in many ways much more advanced, but also it just was 4 and 51, right? Not a huge difference, maybe. And also being at IBM, there's like people visited quite often, working on computing, quantum computers, and sometimes that they would tell me, well, it's just a matter of like a few years because like we know all the tools how to build a computer, we just have to put them together. But still, like as far as we know, there's no real quantum computer, or really, I mean, real. I think already the quantum computer they have at IBM already solves some useful problems, like some simulation problems that you couldn't do otherwise. But I guess for cryptography, it's still like a bit out. Luckily, that the things can be broken. But still, I think we should not, like wait and be pressured. And so, yes, I mean, a lot of quantum safe crypto is still, I mean, there's a lot of stuff exists, but if I had to get the team to replace like all the crypto that we have on the computer with quantum safe crypto, we couldn't do it, right? So there's still more work needed there. And obviously that's work that needs to happen in the near future. So I guess that's one thing that we need to do. I think there's another thing that as cryptographers we need to do better, and it goes back to this like toolbox kind of thing. Because very often what we have, so we have signature schemes, we have encryption schemes, but if we really want to compose them, so it's like we still need more there. And what I mean here is in terms of security definitions, because the definitions that we like the way we prove security is you have like this overall system, so that's how it is secure, but then you try to break it down. But very often you end up with like one gigantic proof because you can't really break it down because it is like things interact in a way that you can't really modularize. And so because like another big thing that needs to be addressed is like how can we do modular protocol, because like in software engineering it's all modular, it's all libraries, right? Use this library, you do that library. But if you would listen to a cryptographer, that doesn't, I mean, we don't know how to make that secure, because now this library might interact with each other in some ways that are people haven't thought about. And so there's a lot of these difficulties that, like very practically, that come up if you build large systems. And I think here we need like more crypto theory, and actually also like the definitions. I mentioned like we still don't know like what a good encryption scheme is in some sense, right? Or I mean, and the same thing here, right? How can how do I have a definition that really composes easily with other definitions? I mean, it's a non-trivial problem, but I think that's also something that needs to happen. And even more, like if you build, like, as we do now with the inner computer, at the end of the day, you want to have like a formal verification of that, but not only like proofs, but maybe a formal verification of like what you like specified and proof secure. It's not, it cannot be the bits and bytes how you end up implementing. Also, like going to your prior point, right? Like these curves, how they interact. But you want to at least have some formal verification. I think there's a lot of work there still to be done, how to build like secure systems.
That's great. And obviously, NIST has had many competitions. I think Daniel Bernstein published a paper recently about the usefulness of competitions. And one of the competitions was the post-quantum cryptography one. And we're starting to see papers arriving on Lattice. Luckily, it hasn't really broken Lattice, but it's good to see the code-based ones coming through now. It looks like they could be the next ones, but we look very dependent upon Lattice methods. So how do you think the post-quantum agenda will change?
Well, I don't really know. Like I'm sort of lost a bit touch with the space because you seem to know more about the recent developments. Because all I know, I need to hire some more people in that space very soon, so we can either do it ourselves or have like the cryptographic communities to the help. It's probably going to be a combination because like like we need very specific schemes, right? And these need to develop. I really don't know, right? I mean, I hope. I mean, I've seen a lot of things happening that, like, when I talk to people at the real world crypto, actually, like about some of the recent developments, I was really pleased to see what has happened in the time I lost touch, like in the more specifics, and yeah, hopefully there's much more will come. I mean, much more needs to come, I guess, as well.
Yeah. Yeah. So if you were to give advice to technical innovators about how they should develop their innovation, what advice would you give them? You've obviously seen a small business grow, and some of the pains that you had growing. If you were an inventor, what advice would you pass on to someone in that situation?
Yeah, I guess the probably it's trivial advice, but I think it's never give up. Like believe in
Yeah.
yourself, never give up. You'll find a way to solve it eventually. I think that's like the number one for doing research, right? You'll have hard days. You maybe thought you had a solution, but then you break it, or your colleague or friend breaks it, right? I think it's you just never give up. Like have that staple of things that if you can't solve it today, maybe you'll solve it next week. Maybe you turn your attention to something else in the meantime. But like never give up. You'll find a solution eventually.
Yeah, yeah, that's great advice. And if you were to change one thing about your career, what would it be?
It's a great question, but I don't know, right? I mean, I think I'm pretty happy with where I am today. I've no regrets, really. I mean, obviously there's like mistakes that you can avoid, right? But on the other hand, you also learn from your mistakes, and not having made those mistakes would not, would make me a different person. So do I want to be a different person? No, I don't think so. I'm pretty happy. So it's like it's all good.
Yeah, yeah. It's maybe a Swiss attitude to life. And what advice would you give to technology engineering graduates who are near to graduation about the skills and knowledge they need to pick up?
Yeah, I think one and probably the same thing. Never give up and believe in yourself. Don't let yourself be fooled. Like I think sometimes I tell people like just bloody hell, use your brain.
Yeah.
You have a brain, just use it. Because other than that, like I guess look for like what interests you, what fascinates you, because you want to have fun, like the way you work. It's a privilege as well. Like not everybody can choose to do so, can have the privilege, but if you can, I think that's really like just makes your life way better. And then maybe the second thing is, of course, like not everything that is fun you can live from. So you still want to have something where actually you can be relevant, where you can make a difference, where you can contribute. And that typically then also allows you to make some money and earn your way of living, and then like, have the best of both worlds, like have fun, to do something that you care about, and then enjoy your life as well.
It's great. I've got one more question, but I just need to ask you about your backdrop there. Could you explain what those are
Sure. I
behind
mean,
you?
those are like the I guess in crypto it's like the OG degenerated things. It's like NFTs, just like bits that you can buy for sometimes a ton of money, sometimes less. I guess I didn't spend so much money as like some of the crazy people before me, like on this like Ethereum NFT board apes with sometimes a million. But it's about having fun as well, right? It's doing something that it's funny, that like people care about. It's like a bit community building, having fun together, really. And it's really, I think it's about that, and it's also I wanted to show that like the internet computer that we build, right? There's the people on top of that, and there's some people that build marketplaces for NFTs, also like everything on chain. You can store those pictures actually also on chain. And I just wanted to also show them, hey, I guess you're doing great work, and it was like like I can't display a chat application on my background. I can display some NFTs. There's a fun, right? So some of them are like I guess I can maybe move them over. You see the one on top, like the Bitcoin flower,
Oh
the
yeah, it's
Ethereum
cool.
flower, and Internet Computer flower. But actually, these are like by an artist who I'm not sure whether he lives in Paris, but he has like street art in Paris. Like this Bitcoin flower is also in a house in Paris, which is also fun. So it's about
Yeah.
like a bit fun culture, like beside all the technology that it can be used for.
Yeah, but it's sensible when you think about it. It's a cryptographic proof that someone owns something, and you can verify that, and then you can transfer that onto someone else. So to me, it's taking wet signatures, and I still create documents with a wet signature that's a GIF, and I paste in, and I have other people's GIF file, and it's a false world. So to me, the NFTs are just the start towards tokenization and understanding how we can cryptographically prove an asset.
Yeah, totally right. And it can be real world assets, it can be digital assets, and like
Yeah.
even art in some sense, right? I mean, like I guess the brush today is digital, and I mean, like that, you can really own the art. You could, if you have it on chain, you could even have like like lend it out to a museum, like give them a museum the right to display it for a short bit, and then I guess later on you can display it again at your home or something like that. So it's all like because it's smart contracts, it runs like in a secure environment. You can really control that ownership of digital stuff, right? And it's like that's and really NFTs are the playground, as you say, for that, for like playing with new technology, and it will change the world quite a bit, as you will see.
Yeah, yeah, I agree. And so my last question is if you were a new researcher, you'd started your PhD all over again, what problem would you address?
Yeah, I'm not sure whether that would be fun or not, like starting all over again. But I think I mean I think it would. Uh, I mean, I guess I would obviously dive into like all this quantum safe crypto. There's like a ton of cool maths to do there. Still like a wide open field, the great advances lately. So I think that would be totally cool. I would, of course, go into blockchain as full compute, like building like in this like internet computer project. If I would learn about that, I would totally want to be involved into that, right? I mean, and I think, you know, having a blockchain that really like can replace like normal full-fledged full performance servers. To me, it's also something at one hand mind-boggling, but on the other hand, it's totally doable, right? If people see Bitcoin, think, okay, that's so slow, it's horrible, but that's just like I mean, you can do way better designs, and that's like I would totally get involved to that. And then maybe the last thing, maybe it's like this like trying to address this composition of primitives in the cryptographic primitives in the protocol, because it's there we still fall short, and it's like one area that nobody really. I mean, some people looked into it because there's like Ron Conetti's work. There's other people like Birgit Witzmann. There's like well, I probably also hear a long list of people who worked on that. But it's still not done, right? I mean, we still don't know how to compose primitives into protocols in a way that's like modular, like as I mentioned before. Like maybe that's another thing I would do.
Yeah, I totally agree. So thank you so much for your great work, and keep up the great work at Dfinity, and hopefully we'll see an amazing internet computer being built that's trustworthy and secure. So thank you so much, Jan.
Thanks, Bill. Thanks a lot. It was fun.